That's on? Yep. Okay, so I think I have about 15 minutes to talk, and there's a lot that I could go over, but I don't want to hold people up, so I'll try and make this as quick and succinct as possible. But basically what I'm going to talk about today is some concepts relating to space group and crystallographic symmetry. So before I get into symmetry, I want to talk about the concept of averaging. So averaging is very closely related to symmetry, and it's the reason why symmetry is important. Averaging is also the reason why we're able to retrieve very high resolution information from very low resolution initial images in electron microscopy, for example. So this is a single micrograph image which has been averaged probably a few hundred, maybe more, single molecular images to obtain a class average, and then when we reconstruct our 3D from hundreds of these class averages, we're incorporating many thousand unit cells, and you can appreciate the increase in signal-to-noise ratio as you move from left to right in this panel of figures. Similarly, this gap junction connection structure down the bottom here, where we have a single unit cell, a projection map, and a 3D from maybe 10,000 images, which are 10,000 unit cells, which are reincorporated into that structure. So the more information that is theoretically identical that we can average together, the better the quality of the structural information we get at the end. And so this is why symmetry is important, because symmetry is effectively a form of averaging at the sub-image level. So to define symmetry, an object's defined as symmetrical if when an operation, some form of operation is applied, some form of geometric operation, the result of applying that geometric operation is indistinguishable from the original. And so if we go back to that example I showed on the previous slide again, when we impose symmetry on this ninefold symmetric projection view here, you can see that we again improve the signal-to-noise ratio of the class average. So this is indeed a form of averaging. And this is why symmetry is really interesting and really important. So the concepts I want to go over today are what is symmetry, how do we identify it, and how do we take advantage of it in electron crystallographic image processing. So before I get to crystallographic symmetry, I'll mention very briefly molecular symmetry. So those of us that work in single particle analysis or perhaps other structural biology fields will be very familiar with the concept of molecular symmetry, which is very closely related to crystallographic symmetry. Basically, the same symmetry operators apply. However, molecular symmetry is predominantly point group symmetry, and it basically describes symmetry operations which can be taken advantage of to average and reconstruct our structures in 3D at high levels of symmetry. There are basically 5 different types of molecular symmetry that we usually see. They can be subclassified into cyclic symmetry, as can be seen in this C5 complex on the right. Dihedral symmetry, like the structure of GRO-EL, which is a very well-known one, where we have 2 symmetric rings stacked on top of one another that are related around a normal 2-fold rotation axis. And then we have higher order symmetries like tetrahedral symmetry in this ferritin structure, which contains light and heavy chains. This heat shock protein has octahedral symmetry, and finally a lot of viruses contain icosahedral symmetry, which is 60-fold symmetric averaging. So that's all I'm going to say about molecular symmetry. I'll need to introduce it. Now I'm going to move on to crystallographic symmetry for the vast majority of the talk. So in terms of crystallographic symmetry, we can think of a crystal as something that is generated, and particularly a 2D crystal as something that's generated by taking a minimum repeating unit. This repeating unit is called a unit cell, and basically consecutively shifting this ad infinitum along either of 2 vectors. This is the theoretical crystal. So in theory, a theoretical crystal has no boundaries. In practice, it usually does, and it has a finite size. But in theory, this pattern is repeated to infinity along 2 crystal vectors, A or B, and these vectors are defined by an angle which is included between them of gamma. And so for this reason, all crystals have at the very first point translation symmetry. So this is our structure of interest that we're trying to crystallise, and this is, in this case, the asymmetric unit. This is a single protein molecule, perhaps, depending on the way this protein molecule is constructed. Sometimes this asymmetric unit represents the unit cell, sometimes it doesn't. If we have non-symmetric arrangement of the 2 proteins within our unit cell, like the example shown here where we've got a chiral molecule and it's reflected, the unit cell is actually the combination, the dimer, if you like, the crystallographic dimer of those 2 unit cells. And then by taking this unit cell and producing it along the vectors which define the unit cell, initially the B vector, which by crystallographic definition points to the right, and then also the A vector, which crystallographic definition dictates that it points down, and taking the included angle between them, we can basically build up a 2D array of our unit cell and repeat this until we end up with our crystal lattice. And as I said, theoretically this goes on to infinity. Okay, so crystallographic space group theory is basically a class of mathematics called group theory, and I'm not going to go into too many details of it other than to acknowledge that that's what it is. But basically a crystallographic space group we can consider as a mathematical group of symmetry operations which apply to both a given unit cell and the crystalline array. So it's a group of symmetry operations which we can basically use to recover through a number of symmetry operations, a number of averaging operations, all of the information that's within our crystal lattice. There are a finite number of crystal packing arrangements, and so this means there's a finite number of crystallographic space groups. In 3D, there are 230 possible crystallographic space groups if we consider all the crystal-compatible symmetry operations that take place. However, many of these contain things like points of inversions and mirror symmetry, and as you would all know, proteins are incompatible with these symmetries because the reflective version of an amino acid does not exist in nature. So there's, in fact, for proteins and chiral molecules, there are only 65 possible symmetries out of these 230, and when we reduce this to 2D crystals, which is what most of us are working with here, there are in fact only 17 plane groups which describe all the possible symmetry groups which exist for 2D crystals. I'll talk a little bit later on about the concept of 2D space groups and how these relate to plane groups as well. Okay, so I'm just going to briefly identify, some of this may seem really basic, but I'm just going to briefly identify the different types of symmetry operators that are present, and then I'm going to show how these give rise to the 17 different 2D plane groups. So the first and most basic symmetry operation, I guess, is the operation of rotation, and this is effectively defined by the fact where we have an n-fold rotational symmetry axis or point in 2D, and this is defined by the fact that taking 360 degrees and dividing it by n, rotating by this number ends up with a result which is indistinguishable from the original. So in the example, the basic example here of this letter S, it's a twofold symmetry because if we take 360 and divide it by 2, we have 180 degrees, and rotating this through 180 degrees gives us something indistinguishable. The same for these higher order symmetries of 3, 4 and 6. And you may notice that I omitted 5 here. And the reason for that is that we can have 5-fold symmetry and indeed higher symmetries in molecular structures, but in crystallographic structures we can't. The reason being, as shown in this little diagram on the right-hand side here, that when we form a crystal lattice, it needs to be perfectly reproducibly packed and tightly packed, and we can't have any gaps in there. If you try to take a 5-fold structure and generate a 2D crystal lattice with no gaps, you find that you can't do it. Similarly for 7-fold and everything higher. So in fact, 2, 3, 4 and 6 are the only rotational symmetries possible in 2D crystalline space. Moving on to unit cell geometry. So this is the shape of our unit cell. It's defined again by these vectors A and B, and this included angle gamma. And for 2D crystals, there are 4 different unit cell geometries. The most basic of these is the rhomboid geometry, which is commonly referred to as oblique or monoclinic. This is where we have the vectors A and B not being equal in magnitude and gamma being greater than or equal to 90 degrees. So this is the general definition of it. And we get into more special cases. The rectangular case here is where A and B are not equal, but gamma is equal to 90. The square case or tetragonal case is where A and B are equal, and gamma is also again equal to 90. And then finally, the case on the right-hand side here, the rhombus or the hexagonal crystal form, where A and B are still equal, but gamma is equal to 120. And obviously, you'll see that these are compatible with different rotational symmetries. Now, the rectangular unit cells are a very special case. That being because rectangular unit cells are the only type of unit cell which can give rise to what's called a centered crystal unit cell. So to illustrate this point, I've got this dot of consider these as maybe protein molecules within a crystal lattice. And if we take a primitive cell, and the primitive cells describe 15 of the 17 possible space groups, what you usually see is that this repeating unit is located at the corners of the cells. And if you take roughly a quarter of this repeating unit in each corner, then you end up with one full asymmetric unit or one full unit cell. In the rectangular crystal cover, it's possible to also have this centered face group, and that's basically where we have internal repetition within our unit cell. We've got a full copy of this repeating unit in the middle, and then again, we've got a quarter at each corner. And the reason for this is going to become apparent later on, but basically it's to do with increasing your chances of increasing your symmetry averaging and increasing the quality of your structure. So this is an experimental example where we have a particular porin molecule which is involved, which forms several different crystal forms, 2 of which are highlighted here. One of them is a primitive cell, and the other is a centered cell. So the one on the left here, you can see the unit cell defined here, and you can see the minimum repeating unit, which actually contains 4 molecules arranged in distinct orientations, outlined in green here, occupies all of the unit cells. So we have no internal repetition in this structure. However, the structure on the right-hand side over here, you can see that this minimum repeating unit is actually this dimeric arrangement of the porins. And so you can shift one up here, you can shift one here, you can shift one here and one here. And indeed, you can define a primitive cell which will do this, and hopefully that's going to come up first. They both came up at the same time, damn. This is the primitive cell that defines this, and so we can move this way, we can move it back here, and we can move it to the side and reproduce that pattern, but there's no symmetry then in that pattern. If we take a centered cell, you can see you can't draw a mirror plane which is normal to either of these A or B axes. But if we take a centered cell, then what we get is an additional mirror axis in here, and so therefore we increase our symmetric averaging. So you can actually take primitive or centered cells to describe a structure in most cases, but usually the centered cell offers more averaging. And so that's why rectangles are special. Okay, so moving on to some more symmetry operations, we have reflection, and this is basically shown in these images down here. It's quite simply a mirror plane down the centre of our unit cell. And when we combine reflection with translation, we get something that's referred to as a glide reflection. And so this is shown in this pattern here. So basically what we're doing is taking our glide axis or our glide line in a 2D image. It runs along the centre of this pattern here, and by moving half a unit cell forward and then reflecting about the glide line, we get a reproduced copy of the image. And so this is what we define as a glide reflection. Okay, so this has basically now summarised all of the symmetry operations that are possible for 2D plane groups. And so by combining all these together, we can rationalise how we end up with 17 possible 2D plane groups. So starting off with our unit cell geometry, we have 4 different unit cell geometries, which I summarise. So the highest order of rotation in each of those, I'll start again. The rotational symmetry possible in each of those unit cell geometries differs. So for a rhomboid, we can basically have 1 or 2. For a rectangle, we can have 1 or 2. For a square, we always have 4. And for a rhombus, we always have 3 or 6. Now, if we then consider the existence of reflection symmetry, we come to the crystallographic point groups that are possible, and there are 10 of these. These are shown here on the right-hand side. And then introducing the concept of a glide reflection, because translations aren't taken into account when we discuss point symmetries. We have a number of these point groups which can have the presence or absence of a glide plane. And so this is what leads to eventually our 17 plane group definitions, which are shown on the right-hand side here. Now, that funny notation that you just saw is something that was resolved many years ago. It's commonly referred to as the Hermann-Malgren style rotation, or the notation, or the international notation. And it basically tells us a lot about the symmetry that's present within the crystal. The first letter here tells us whether we've got a primitive or a centered cell. The second letter tells us about the rotational symmetry of the unit cell. And the next two symbols basically tell us about whether we've got mirrors or glides present. So you can see this one here is discussing symmetry perpendicular to the main translational axis. And then the final letter discusses any additional mirror or glide symmetries that are present that don't satisfy the first criteria. And so these are our 17 plane groups. And you'll be able to look at these for reference, or you can get them out of the international crystallographic tables, or indeed in other places on the web. But this is basically the symmetry operations that are described in those 17 plane groups. Okay, so I said I'd come back to this point here about the fact that we have 17 plane groups in 2D and 17 2D space groups. So just to reiterate what I may have glossed over earlier, basically these 17 plane groups describe the possible symmetry operations that are present for projection images of 2D crystals. So these are true 2D images. Even though 2D crystals are not truly 2D, the projection images of them are. And so there's a lot of symmetry operations that are possible in these 2D images that aren't possible in actual 2D crystals. These are things like reflections and inversion symmetry and stuff like that, which would normally be disallowed because proteins are chiral molecules. Okay, but somewhat trivially, these 17 plane groups actually map to the 17 2D space groups. And so the reason for this is shown in these next two slides. Firstly, if we have a mirror plane present in our crystal, then this basically maps to an in-plane centre of rotation. So you can see if we look at this chiral molecule from the position of the eye here and create a projection map of it, this molecule's been rotated in the plane of the membrane or in the plane into the screen here through 180 degrees. And when we generate the projection map of this, you can see that this basically looks like something that's had a mirror operation applied. And so that's how this particular operation maps in 3D. The second is the glide plane operation, which I talked about earlier, and this basically maps to a screw axis in 3D, which again, many of you would be familiar with. In particular, it actually maps, to a 2-1 screw axis, because there are other screw axes that are possible as well. So basically, again, we just have our repeating unit here, which gets translated by half a unit cell, and because a twofold in-plane centre of rotation equates to a mirror plane, then taking a glide line basically equates to a 2-1 screw axis. Okay, and so basically we come up with the 17 2D space groups, and these are also known by other names, but that's what I'll refer to them as for the purpose of this talk. And as I said, these trivially map to the plane groups, which are shown on the left-hand side. Basically, all we've done is we've taken the mirror planes and replaced them with two-fold rotation axes, and we've taken the glide planes and replaced them with two one-screw axes. So it's pretty simple, really. Okay, so to finish up, I've just got a couple of examples. This is an RC47 photosystem 2 reaction center complex, which has P2GG symmetry, or the 2D space group is P22121. And what you're going to see in the next few slides is basically how you can take this real space image and rationalise the symmetry elements that are present in that space group. So the first of these is a two-fold centre of rotation shown by the magenta diamonds here. And you can see that at the start and the end of this operation, the transparent unit cell, which is being superimposed, basically superimposes perfectly, so it satisfies the symmetry requirement. Secondly, we have a glide plane in the vertical direction, and you can see again that it superimposes perfectly. And thirdly, a glide plane in the horizontal direction. Okay, so one of the neat things about symmetry, so Carsten talked about this very briefly, the concept of signals in an electron microscope being signals recorded from an electron microscope being representative of cosine waves. And so one of the neat things about symmetry and identifying symmetry and applying it is that in Fourier space, symmetry is conserved if it's present in real space. And so there's a number of things that we can look for in Fourier space which will help us identify symmetry elements and the symmetry of the unit cell in real space. One of these is the centrosymmetric condition. So this basically dictates that if a crystal has two-fold symmetry, all of the phases in Fourier space must be 0 or 180 degrees. And this stems from the fact that the only way we can place a cosine wave that is two-fold symmetric about the phase origin of the image is if the phase shift of that cosine wave is 0 or 180 degrees. So this is something that we often look for, and that the programs that perform symmetry calculations look for to identify two-fold symmetry within an image. And it's also something that's used to adjust numbers to the ideal numbers. The second thing we can look for is the presence of systematic absences. This seems to be a little bit out of order, but regardless, I'll talk about it anyway. So systematic absences arise from when we take the situation which I talked about earlier, about how we can have either a primitive cell or a centred cell which describes our crystal lattice. So the example here I showed earlier has internal periodicity, and so what you'll notice is that the A and B vectors which describe this unit cell are different to the A and B vectors which describe this unit cell. And so when you perform a Fourier transformation of this, you'd expect to get different diffraction spots. But it's the same crystal, so you don't get different diffraction spots. The reason for that is that some of the diffraction spots which arrive are known as symmetry forbidden diffraction spots. And so these are diffraction spots that are present, or absent rather, in centred cells, and also present in cells that have glide reflections. And you'll see that in this example, which is the final example I'm going to discuss before I finish up. So these are crystals of aquaporin 1, or CHIP28 it was referred to when it was published. And what you'll see here is that by looking at the phase and amplitude data that's present within this Fourier transform of the crystal, you can adequately resolve what the unit cell symmetry is that's in place here. So the first thing we get is the values of A and B and gamma. So you can see, and there's symmetry forbidden reflections in this, so that's why these arrows seem to be pointing to nothing. Basically, you can get the length of A star and B star, which is inversely proportional to the length of A and B in real space, and you can also get the angle that separates them, and we can use these to define the unit cell. We can also use these to define the shape of the unit cell, and in this case we've got a square unit cell because of the relationship between these. We find that if we look at the phase and amplitude information, all of the phases in this map are equal to 0 or 180, so that means it's a centrosymmetric space group. We find that points related by four-fold rotation are equal. Okay, so this basically means that the base rotational symmetry is P4. And we see that the odd reflections are absent, and this is a systematic absence that's indicative of a glide plane. And further to that, the fact that spots equidistant from A star are out of phase by 180 is another indication that we've got glide symmetry present in this particular crystal. There's a couple of examples of that there. So when we go back to the real space image, what we see is this. And what you'll find is that all the symmetry elements that we just identified in Fourier space are actually present in real space. And so the space group of this crystal, which has four-fold rotation symmetry, one pair of glide axes and a pair of mirror lines, is P4212. Okay, so the final thing I wanted to mention is Allspace, which is the program that is used in the MRC software to identify symmetry, and it's also the program that's incorporated into the 2DX image processing software. And basically what happens when you run Allspace is you have all of your amplitude and phase data and your spot data collated into a text file, and then it goes and runs a whole bunch of routines to compare these to ideal symmetry operations to work out what the unit cell is that you have. And so here we have a list of all of the possible space groups in 2D, and it basically spits out some scores which you can then use to evaluate your symmetry. I realised this morning this is a really bad example because it doesn't pick up any symmetry here. The reason for that is because this is actually a tilted crystal. But regardless, the one thing I wanted to point out before I finish here is that there's 21 lines, even though we only go down to 17, there's 21 lines in this particular plot. And so that may be a source of confusion for anyone that digs out the Allspace plot when they're processing their crystals. The reason we have 21 space groups is because for some of these space groups, but not all, the direction of the A and the B vectors is important. And if you index your crystal back to front, what happens is it still picks up the symmetry, but it tells you that you've got it back to front, and you can go back and correct that later on. So that's why we have 4 additional space groups. And finally, some other considerations, which, as I said, I won't have time to go into today. But what's important to think about when you're working with 2D crystals is when might symmetry fall apart. So as I showed in that previous slide, plane group symmetry only holds if you have untilted specimens. Once you start to tilt away from zero, the symmetry falls apart. Astigmatism also has a non-uniform effect on your spots, and so unless you're doing correct CTF correction for the astigmatism, it can have an effect on your symmetry evaluation. Symmetry rules only hold when data is shifted to the phase origin, and things like stain exclusion patterns and low resolution data may cause you to overestimate your symmetry. So it's important when you're processing and merging data that you continually check for the presence of symmetry and make sure that all of your data is always self-consistent. One final note is that Allspace does not use systematic absences to evaluate space groups, and so this is something that you can do manually. If you observe systematic absences within your space group, you can use this to make sure that the symmetry you're implying is actually the correct one and that Allspace hasn't picked up a false positive, if you like. So that's it from me. As I said, it was only a short talk today, and so I'll direct you to some further reading. On the left here is Bob Glazer's book on electron crystallography of biological macromolecules, which has a really good chapter on symmetry on it, as well as lots of other really useful information, and I think Richard plugged this yesterday. There's also a review that's in Journal of Structural Biology, which is about 3 years old now, but which basically goes through everything I've presented in this talk and goes into a lot of stuff in a lot more mathematical detail. So if you're interested in going into this into more detail, then I'd recommend looking at either of those 2 sources, one of which is much cheaper than the other at the moment. So with that, I'll finish up, and I think it's time for coffee. Yeah.
How reliable are the automatic procedures in order to find the symmetry in normal imaging conditions? Do they normally work? Do you have this feeling that
So treated correctly, they normally work. There are many examples where it will pick up an incorrect symmetry, and I think the onus really is on the user to go back and check that everything's self-consistent, that sub-symmetries are being satisfied, that the symmetry is present in multiple different images, and even looking at real space maps and making sure, I was actually talking about this with Daniel yesterday about when you've got Daniel Levy, when you have biological criteria which you know are satisfied, which would break the symmetry that you have present. So if you know, for example, that for the biological function of something in a crystal cell, that it has to be arranged in a certain symmetric way, and then symmetry you get out is different to that, then you really need to think about whether you trust the biological data or whether you trust the data that comes out of the computer. And so there are some examples where it will pick up the wrong symmetry, but it's very easy to treat it correctly and treat it thoroughly. It's very easy to identify those incorrect symmetry assignments, and they shouldn't pose a problem.